of Change, a podcast from Duke Engineering dedicated to the ingenious ways engineers are solving some of society's toughest problems. I'm Michaela Kane. This episode's topic involves a subject that's been hard to avoid this year.
A pandemic that has turned our world upside down.
The coronavirus pandemic.
Coronavirus. COVID-19.
Being a coronavirus.
Back in late February and early March, most people could say that the novel coronavirus wasn't significantly affecting their daily lives. But that wasn't true for Casio Fontes, a PhD student in the lab of Ashutosh Chilkoti in the Biomedical Engineering Department at Duke University.
So, sort of in late February, as we realized that coronavirus was here, this was going to be a serious problem, I approached my senior graduate student, Casio Fontes, and I said, perhaps we should take a little break, a little detour, and see what we can do in terms of coronavirus diagnostics. And Casio is very adventurous and works very hard, and he jumped on it.
I was actually home writing my thesis, right? And because I've been at Duke for quite a while and it was time to graduate. And then Tosh was like, oh, come back and we need you to work on a test, see if you can make something quick.
The test Fontes is referring to is the D4 assay, the lab's signature diagnostic platform. It's made by inkjet printing an array of antibodies onto a glass slide with a non-stick polymer brush coating, and it has the potential to transform point-of-care testing into an easy, accurate, and fast process. There are lots of different types of diagnostic tests. The gold standard is the polymerase chain reaction test, or the PCR. The PCR works by copying a target stretch of RNA or DNA until it can be detected in a sample. This test is highly sensitive and accurate, but it isn't portable, and it requires trained technicians to use. On the opposite side of the spectrum are lateral flow tests, which are similar to a pregnancy test where you can add your sample to the platform and get a diagnosis very quickly. But the trade-off is diminished sensitivity, so they aren't as accurate. But the D4 assay operates at the intersection of these tests, offering sensitivity and portability, and shortening a wait time of days into less than an hour. Chilkoti and his lab began developing the platform more than 15 years earlier, but they hadn't actually intended to create a diagnostic test at all. Instead, it started with the creation of a polymer brush coating that prevented cells and proteins from sticking to its surface. One of the many challenges of working with diagnostics involves cutting down on the background noise in a sample. This means that while some diagnostic tests may pick up the target protein, they may also pick up other proteins that you don't want to capture. Or they can show a positive signal even when no target protein is present, and all of this muddies the test result. But the nonstick coating seemed like a promising solution to this problem.
And the hypothesis was that because we had a surface to which nothing stuck accidentally when you didn't want it to, if we attached some sort of capture molecule like an antibody to the surface, we should then be able to pull out a protein of interest from a complex mixture like blood or serum. So we'd have very specific capture where we wanted it, when we wanted it onto this non-stick surface. We could really get rid of this background adsorption problem that has plagued all immunodiagnostics, because a lot of diagnostics are done by putting a molecule on a surface like an antibody, which then pulls out whatever you want, and then you detect it. That was our hypothesis, and so we started to work on it. And I had a student, Angus Hucknall, one of my most creative students, I would say, who discovered a way to make it work, where what he discovered was that once you made the surface, you really couldn't do any other chemistry to it. If you did any other modifications, no matter how subtle, you'd ruin this non-stick behavior.
Hucknall realized that if he dried the surface, he was able to inkjet print the antibody onto the slide so it could be captured within the polymer surface.
That was sort of a very counterintuitive idea he came up with. And by doing that, he wasn't doing any chemistry on the surface. There was no chemical modifications we made, which meant that the background, the rest of the surface remained pristine and therefore completely repellent to proteins and cells.
By figuring out how to add these capture antibodies into this polymer brush coating, Hucknall was able to create a sandwich immunoassay, which works by capturing the target protein between two antibodies, like peanut butter between two slices of bread. When a sample is placed on the slide, the antibodies capture the target antigen between them and light up. These spots of light can then be read using a small handheld scanner.
And what he showed was you could get this really intense spots, very clean spots, no background, and we could improve the performance of given any sandwich immunoassay by 100 to 200 fold, right? By just getting rid of this background adsorption problem. That was the first development. And then his PhD, he did something equally interesting where he decided to move into point-of-care diagnostics. And we decided to do this because we both recognized that we were working on these surfaces where these spots that we were inkjet printing were like 150 microns, about the width of a human hair. So we had these tiny little spots we were printing, so we didn't need very much blood to do the assay. We could do it with a drop of blood. It was a very simple idea, but it worked beautifully. And so 7-8 years later, we published another paper in PNAS showing this idea and showing that despite creating this very simple assay, we actually didn't lose any performance. So we could now do a point of care test without losing any sensitivity. This has been another big challenge in point of care assays is when you go from a central lab setting to a field setting or a point of care setting or a self-test setting, you often take a big hit in sensitivity, and we did not.
When Fontes joined the lab in 2014, a very different virus was drawing the world's attention, and it prompted him to pursue the project that would later become the basis for his PhD thesis.
2014 was when the Ebola outbreak happened, and that's when I sort of like jumped into this project of making a new test for a new biomarker on Ebola.
Because the Ebola virus is only contagious after patients develop symptoms, doctors relied on sensitive tests, like the PCR, to identify and quarantine patients who tested positive for the virus. But Fontes and his collaborators across Duke and at a BSL-4 lab in Galveston, Texas, wanted to see if the D4 could detect a biomarker that was present in blood before symptoms appeared.
And the test is like really cheap and easy to manufacture, so you could potentially like mass screen populations, right? Like there was an outbreak on a village, you just screen everyone on the village, and then you can actually like identify people that are infected but are asymptomatic still before they develop the symptoms, right?
Although the speed, portability, and sensitivity of the D4 makes it an ideal platform for tracking disease outbreaks in resource-limited settings, Fontes' work with Ebola also proved that the D4 assay was a great platform for screening antibodies and other reagents, which helped researchers identify which materials were the best match for different antigens.
I sort of like jumped into this project of making a new test for a new biomarker on Ebola. But to make that test, I had to develop like a bunch of different technologies to like integrate new reagents, screen new reagents, develop new reagents for Ebola because it was a new biomarker, and antibody development takes quite a while. And a good chunk of my work was actually figuring it out how to streamline the development and selection of these antibodies. And the D4 was actually like a key role it's like the centerpiece to like expedite this antibody development.
When the coronavirus was identified as an emerging global threat in early 2020, the Chilkoti lab recognized that their previous work with the assay made it an ideal platform to test for the new public health threat. The team was able to collect a multitude of antibodies and other reagents to test, including antibodies from the original SARS virus, which is another coronavirus that was responsible for an outbreak in 2003.
Dropped everything else and started to play around with these reagents to see what kind of diagnostics we could develop.
The team was able to create a proof of concept that could accurately detect biomarkers from a synthetic version of the SARS-CoV-2 virus, which causes COVID-19. In recognition of this work, they were awarded a Rapid Response Research Grant from the National Science Foundation to continue to optimize and validate their platform. This work also involves exploring how they can make the diagnostic easier for people to use in the field, whether that's in places like West Africa or at the Duke University Medical Center.
If you have a drop of blood diffusing on a surface, you want it to be enclosed. I mean, after all, let's say you're detecting Ebola virus, you don't want the tester to get Ebola. It has to be completely self-contained and safe. So I have a student, David Kinnaman, who's done an amazing job in building a self-enclosed, what we call a passive microfluidic chip.
Here's David Kinnaman to explain.
Our goal has been always, can we add the sample and then the chip does everything else for you? So essentially, what the microfluidic chip does is the incubation, the washing, and the drying all by itself. And we wanted to accomplish that in what's called a passive way, meaning we don't have any sort of power supply, any sort of actuators, any sort of pumps that accomplish this task. We don't want to have some sort of secondary piece of equipment that's required to operate those steps. We want it to be able to stand alone in field.
As Kinnaman redesigns the microfluidic chip, they've also recruited Jake Hegestad, another PhD student in the Chilkoti lab, to adapt the D4 to perform both antigen and serology tests to detect COVID-19.
The reagents were not great, but they were good enough for us to certainly develop a diagnostic to test for the disease. but also to develop a diagnostic to look at the antibody response, right? Because after you get the disease and you recover, you then, you develop antibodies which may be protective. And so that's called serology. And so these are the two important tests to diagnose people, newly infected people, but then also to look at and see in convalescent patients, are they developing antibodies, which could potentially be protective? And we realized that we could potentially do both.
I mean, the idea with the antigen test is it would be something that could be used for acute diagnosis. So if someone's actively sick with the disease, you could hopefully go in and get tested for these different antigens that we're trying to detect for. Whereas for serology, we're actually trying to detect, previous exposure to the disease. So you're looking for your antibodies response to the virus, which is in the way of production of antibodies. So if you can detect antibodies that are specific to the SARS-CoV-2 virus, it is suggestive that you've had the disease at some point.
For the antigen test, I mean, the key thing is we don't need a centralized lab. Like the current nasal swab, you do the swab, it gets sent to a lab where the PCR is done, and then you get results a couple of days later. If our antigen test works as we think it will, we would have results, quantitative results in the frame of 1 to 2 hours, as opposed to 1 to 2 days, depending on where those results are being sent.
The unique thing about our technology is that the way I like to describe it is like we have like the ease of use and the usability of like the lateral flow assays. So like the pregnancy type tests, they're very simple to use. But the issue with those is they're oftentimes not as sensitive or specific to the disease. So because of our platform, we have the usability of those lateral flow assays, but also the sensitivity of traditional laboratory-based assays like ELISA. And a lot of that comes down to basically the surface that we're using. It's a high-performing surface for these clinical diagnostic tests.
According to the team, the goal is to test the accuracy of the platform using samples from patients, which is possible due to a collaboration with Chris Woods, a clinical investigator and professor of global health and medicine and the chief of the infectious disease division at the VA Medical Center. They anticipate starting clinical tests this fall.
We have a functioning research prototype for both the antigen and the serology. I would say that the serology is further along. There's reasons why we believe that it could be more useful in the short term, but our obviously long-term goal is to have both tests working well. And when I say further along, I mean we've tried more reagents, optimized more for performance, and tested in simulated human samples for the serology test, while we're still looking for maybe the best reagents to use for the antigen test. We still have a functional test for the antigen, but we do think we can do better.
Although the coronavirus diagnostic is a large focus of their current work, the Chilkoti lab is also continuing to adapt their platform to explore how they can detect a variety of different diseases and pathogens. In April, it was announced that the lab had received 2 grants totaling more than $13.7 million in funding to use the platform to detect bioterrorism agents and to diagnose breast cancer in resource-limited settings. After all, the current global pandemic underscores the need for rapid, affordable, and accurate diagnostic testing.
The platform itself is it's not only like sensitive but it's also really easy to adapt to other diseases. Like you can essentially, we've done cancer biomarkers, we've done several infectious diseases, we've done inflammatory biomarkers. We can potentially even in the future, as the technology develops, make like a panel for 50 diseases in this platform. All you need is like a little drop of blood, and you can test for all of them at once. Mm-hmm. Testing is the first step, right? To figure out who's sick, who's not sick, to isolate people, to start decontamination, even to treat people. And if you're not testing people, if you can't test people fast enough, there's really no way to control any outbreak.
That's it for this week's episode. If you liked our podcast, share with your friends, follow us on social media for updates, and don't forget to subscribe. Thanks for listening to Rate of Change, and until next time, stay safe.